everyone. In this video, I'm going to show you an example of how to think through an equivalence proof. So in this video, I'm mostly just going to be focusing on the thought process and kind of like the scratch work that you would write out as you're thinking about how to write the proof. And then I'll also include a PDF of the finished, polished, fully typed up proof so that you can see how my thinking process in this video translates into an actual written proof. So the basic structure that you'll work through as you're writing your equivalence proofs is you'll first use algebraic expressions to represent the pattern, and then you're going to write an equation to show the equivalent relationship that you're trying to prove. So the equation is basically going to summarize what your conjecture is. And then once you have your equation written, then you're going to prove that the left-hand side of the equation really does equal the right-hand side of the equation in all cases. So it's easiest if you see this in an example. And I'm going to use this example that I shared in the last video about the sequence that my dad texted to our family group chat to show you how this process works. So specifically, I'm going to show that this pattern and this pattern will always create the same sequence. Because we can see here that it's a pretty solid conjecture that they will always meet or create the same sequence. Because with April's pattern, she got a 15, a 35, a 63, a 99. And if you follow her pattern backwards, she didn't write this, but 1 times 3 does equal 3. And so her pattern creates the same sequence that mine does when you do 2 squared minus 1, which equals 3, 4 squared minus 1 equals 15, and so on. So we can see that it works for the first few terms, but we can't guarantee that it will always be the same if you were to follow this pattern out to like the 100th term. It seems like it's likely because it worked for the first 6 terms, but we can't guarantee it until we prove it. And so that's what we're going to do in this equivalence proof is show that April's pattern and my pattern will create the same sequence regardless of how many terms you follow this sequence for. So the first step we're going to do is we're going to write an algebraic expression for both of our patterns. So in April's pattern, well, actually, let me start with my pattern because my pattern's a little bit easier to write the algebraic expression for. So in my pattern, there's only one number that's changing. It's this even number that I'm squaring, but the exponent is staying the same, and I'm also subtracting 1 consistently. And so I just have this one number that's changing. And I want to be able to write this number in terms of a variable that represents which term number I'm on. So this first one was the first term, and that gave us a 3. Our second term was a 15, our third term was a 35, the fourth term was a 63, and the fifth term was 99. So I want to write a formula where I can predict what the nth term is going to be without having n to be a specific number. So like it could be the 100th term or the 57th term or the millionth term. And I want to have a formula where I could figure out what that is. So when I look at this pattern, I notice that the first term has a 2 in that spot in my pattern that's changing. And then the second term has a 4, the third term has a 6, the fourth term has an 8, and the fifth term has a 10. And if you notice, the number that I'm squaring is always twice as much as whatever term I'm on. So for the nth term, I would have 2 times n. And that would be the number that I would square and then subtract 1 to figure out the value of the nth term. And you can test this out by taking, say, like a 3. If I plug that in, well, 2 times 3 equals 6. 6 squared is 36 minus 1 is that pattern that I have right here. And so this is the algebraic expression that represents my pattern. Now, April's pattern is a little bit more challenging because her pattern has 2 numbers that are changing. You have these increasing odd numbers, And then you have the next odd number right after those numbers. So you have like two sets of increasing odd numbers. So to write an equation for this, we need to think about what the definition of an odd number is. And the definition of an odd number is that it's a integer, which often we represent with the letter n, times 2 plus 1. Because even numbers are ones where you just double the integer, and then odd numbers are where you double the integer and then also add an extra one, and that's what makes it an odd number. So if we use this n to represent this n, we could plug it in and see what number we get. So like if I plug in a 1 for n, well, 2 times 1 is 2, plus 1 would give you 3. If I plug in a 2, 2 times 2 is 4, plus 1 would give you 5. So it looks like this expression is representing these odd numbers right here. So I can write 2n plus 1 to represent that number in April's pattern for the nth term. And then I also need to figure out how to express these odd numbers. And what I notice is when I doubled the term numbers, so like when I did 1 times 2 or 2 times 2, these odd numbers are just 1 less versus the green odd numbers that I underlined are 1 more. And so the way that I could write this algebraic expression would be 2n minus 1. Which also represents odd numbers because it's just one offset from an even number, and 2 times an integer will always give you an even number. So in this case, this algebraic expression represents April's pattern for the nth term. So now that I have an algebraic expression that represents both of the patterns that I'm trying to show are equal to each other, now I'm just going to write an equation, and I'm going to say, okay, a summary of my conjecture, which is that April's way and my way always create the same pattern, is that for any value of n, or any term number that we're looking at, these two expressions will always be equal to each other. And this is why it's helpful to use an equivalence proof, because our goal is to show that this is actually always equal to this. We have a conjecture, or we think that that's always true based on the fact that it is true for the first 6 terms, but we need to show that it will be true for any term, whether it's the 100th or the millionth or the 78th term, that these two expressions will always be equal to each other. So this is where the algebra that we talked about in the last video comes in. Because the way that you show that these two things are equal is you simplify the left-hand side and the right-hand side until the expressions are equal to each other. So to simplify the left-hand side, we can use the foiling process, or the process of multiplying expressions. And I can distribute the 2n to the 2n, which gives 4n squared. Then distribute the 2n to the positive 1, which gives positive 2n. Then distribute the negative 1 to the 2n, which gives negative 2n. Distribute the negative 1 to the positive 1, and you get negative 1. And this can actually be simplified further because a positive 2n plus a negative 2n will give you 0 n's. And so they cancel each other out through addition, and you end up with 4n squared minus 1. Now, this expression is very similar to the right-hand side, but they're not quite equivalent yet. So on the right-hand side, the way that I would simplify this one is I would say, okay, well, I have 2n squared, which means that I have 2n times 2n, and then I subtract 1 from that. And 2 times 2 is 4. N times n is n squared. And so 4n squared minus 1 is a simplified version of that right-hand side. And as you can see, the left-hand side and the right-hand side simplified to the same expression. And so we can say that those two are equal, and they will always be equal regardless of what n is. So whether we're talking about n equaling 100 for the 100th term or 99 for the 99th term, my pattern and April's pattern will always be equivalent to each other because I've shown algebraically with these generic expressions that involve n, that the two patterns will be equal. So, to review, the structure of an equivalence proof, or the way that you write an equivalence proof, is you use algebraic expressions to represent the pattern. Then you write an equation to show the equivalent relationship. And then you prove that conjecture that the left hand side really does equal the right hand side of the equation in all cases. So I will also post a PDF of this written up proof because this video just kind of outlined the thinking process for it. But I'll also upload a PDF so you can see an example of what the proof would look like for this situation. So thank you so much for your time, and I hope you have a good day.